In this video, I'm going to talk about the free electron gas. And the material I'm going to talk about is going to be from the Griffiths Quantum Mechanics 3rd edition. So if you have stumbled upon this video or you have searched up free electron gas, you might have found my video. And the difference is that in my video, I'm going to go through every detail. So if you look at the textbook, it actually skips a lot of math steps. It doesn't explain how does one leads to another, like it's sort of disconnected. But in my video, I'm going to talk about every single math step with no skipping steps. So if you follow along, you understand how this all connects and there is no missing math steps. So I hope this can be more intuitive than you reading the textbook. So let's talk about it. So the object in question is a rectangular solid. So we have a rectangular solid, and let's say it has some axis. So let's say this is the x-axis, this is the y-axis, this is the z-axis, right? Then this side will be Lx, this side will be Ly, and this will be Lz, right? And these lengths correspond to the width, length, height of the rectangular solid. And now we need to imagine an electron inside that experiences no force at all, except at the impenetrable wall. So what does that mean? So let's take a look at our Vxyz. So our Vxyz, so our potential energy, is going to be 0. So 0x Lx, what we're writing here is the constraint. Y, Z, right? So this, and we have infinity otherwise. So what we have top is the constraint. So basically what this says is that when the electron's inside of the rectangular, which is we're setting the boundary here, it experiences no force at all. And this infinity implies that the electron cannot exist outside of the box that we have constructed. You might have seen this also in chapter 1 or 2, or there's the case of infinite square well. They did similar to the same thing, how they made the potential energy outside of a certain area to be infinite, so that would imply the electron cannot exist outside of whatever boundary you set. So that's what we're doing here. We have defined the potential energy and we have set the boundary. Now we can take a look at the Schrodinger's equation. So the Schrodinger equation says negative h squared over 2m Laplacian psi is equal to E psi. So what we're going to do here is that we're going to assume that we can break our wave function into x, y, and z component. So our so our psi x, y, z is going to be equal to x, x, y, y, z, z. And you're going to see why we're doing this very soon. But what we simply do here is that we simply assume that our wave function can be broken down into a 3 different product of individual function, which their variable is their own spatial coordinates. So I've broken our wave function into x, y, z components. Simply put, that's what I did here. Nothing more to it. So for our x, let's take a look at the case. So for our x, it's going to be, if we plug this into our if we examine our Schrodinger's equations or our psi here in xy component, what are we going to get? So we're going to get, so for x, we're going to get negative h squared over 2m Laplacian. No, not Laplacian here, because there's no longer Laplacian here, because if we separated the xyz into 3 different spatial coordinates, so in this case we're dealing with x. Since we're only dealing with x, so there's only one variable, so the Laplacian just becomes a simple differentiation because there is only one variable, like the partial is for multiple variables, if you understand what I'm saying. So this is going to be ex x, and we follow a similar logic for y. and similar logic for Z. Z. And since we are breaking the psi into 3 parts in terms of x, y, z, we're gonna do the same for energy here, right? So energy of ex, ey, and ez, and intuitively the total energy is just going to be ex plus ey plus ez, and this is also what the text wrote. Right, so we have done nothing complicated so far. So far we have defined the potential energy for the scenario we're considering, and we have looked at the Schrodinger's equation, broken down our Schrodinger equation into 3 spatial coordinates x, y, z, and then plug those into our Schrodinger's equation and see that we have 3 different equations for independent spatial coordinates. That's what we have done so far. So everything makes sense, is intuitive. So now we're going to come across the first step that the textbook skips, that leads us to so-called kx. You might be wondering where that comes from, but I'm going to explain. So let's first take a look at this, right? So if we move this down, it's going to be negative h squared 2m d squared x dx squared is ex xx. So what we're gonna do here is that we're gonna rearrange the equation. So now we're gonna move let's move this negative h squared over 2m to the other side. So d squared x dx squared is equal to ex xx over negative h squared over 2m. So this is gonna give us, we're just doing some algebra right here. So this is going to give us negative 2m ex h squared times xx. This is what we have here. And now if we move this whole thing to the left side, this is going to give us d squared x dx squared plus 2m ex h squared xx is equal to 0. So this is what we're gonna get, right? And what we have here is a second order differential equation, right? So the solution to this is that if we can define a variable here called kx, which is gonna be whatever we have here. So kx squared is gonna be equal to 2m e over h squared. So this will just turn into the following: d squared x dx squared plus kx squared xx is equal to 0. So that's what we have done. We have replaced, we have took this 2m ex over h squared and then make that equals to kx squared. So similarly, we're gonna do the same for y and z, but they all follow the same logic. So what I'm gonna do here, I'm just gonna skip the step. So ky squared 2m ey over h squared. So for z is gonna be kz squared is equal to 2m ez over h squared. Is what we have, right? And if you're wondering where this come from, where the y and the z come from, you can simply just repeat the same step that I did here. So why did we choose kx, ky, kz? Why do we have to define a variable? If you ever taken a physics course, especially a course about like pendulums and harmonic oscillators, when you look at this form, what do you realize? You realize that this is familiar because it's simply the same as the differential equation you dealt with in the simple harmonic oscillator and the standing waves. And we know the general solution to this differential equation, right? Because we have dealt with this in simple harmonic or other scenarios. So the solution to this differential equation is going to be x is equal to ax sine kx x plus bx cos kx x. So this is going to be the solution to our differential equation. So the same applies to our y and z, right? So for our y, it's going to be y is equal to ay sine ky y plus by cos ky y. So for our z, it's going to be the same thing. Again, so this is much more convenient instead of doing each one of them again. Since you understand what I did for x, the same logic follow for y and z, right? So z cos kz times z. So we have these three formulas. So now, before we talk about the boundary condition, let's look at our energy again. So remember, our energy was E equal to Ex plus Ey plus Ez, so three different components. And if you take a look at this formula, so Kx, x at the bottom, not multiplied by x. Sometimes I write too fast and it seems like I'm multiplying k by x, but x is actually just a component. It defines, you're not multiplying by x. So kx squared is equal to 2m ex over h squared, right? So what we're gonna do is that we're gonna isolate ex here. So kx squared times h squared over 2m is gonna be ex. And the same logic goes for ey. So ey is gonna be ky squared times h squared over 2m. Ez is gonna be kz. Oh, what happened to my? Just make this bigger. Kz square times h square over 2m is what we have here. So if we plug these each one of these into this equation, it's going to give us E is equal to h bar square over 2m k x square plus ky square plus kz square. So we have the formula for the total energy. But let's continue on the next part, which is the boundary condition. This might be the more confusing part. So what does our boundary condition tell us? So let's write boundary condition. So for a boundary condition, we know that the particle cannot exist outside of the box. So the wave function vanishes at the walls and beyond. So mathematically speaking, what does that mean? That means that at what point, so for our x, y, z, if we want it to be equal to 0, what does this happen at? Well, this happen at x equal to 0, right? X is equal to Lx because when it's at the edge, it's equal to 0 because it vanishes. And y is equal to 0, y is equal to Ly, z is going to equal to 0, z is Lz. Yeah, that's what we have here for the boundary condition. So once we have our boundary condition, we could look at how they affect our wave function. So remember, our wave function was x, y, z is equal to x, y, z, z. We have already done this, right? So each of our component xx, yy, and zz must independently satisfy our boundary condition. So let's examine our xx first. So at 4 x, so we're only looking at xx here. Then if we figure out the xx, we can apply the same to yy and zz. So at xx, at x equal to 0, x0 is going to be equal to 0. At x equal to lx, lx is equal to 0. Right? Because this is our boundary condition we have literally just listed here, is what we're doing. So we know the general solution is ax sine kx x plus b cos kx x is what we have as the general solution. So let's look at what happens at x equal to 0. So at x equal to 0, when you plug in 0 as the variable x here, you get ax sine 0 plus bx cos 0 is equal to, well, sine 0 is just going to be 0, right? So this term vanishes, and this is going to be equal to 1 times bx, so this is equal to bx, which is equal to 0. So what does this tell us? This tells us that bx is equal to 0. So that's pretty important information, because if bx is equal to 0, we can simply just eliminate this term from our solution, because we know bx is equal to 0. It doesn't matter what cos kxx is, right? This latter term just becomes 0 and vanishes. So we're left with ax sine kxx. So we're left with ax sine kxx. This is what we're left with. And let's look at what happens at x is equal to lx. At x equal to lx, so we have this equation here. So lx is equal to ax sine lxx, and then we know that this is equal to 0. So if we look at this equation, ax sine lxx is equal to 0. This implies sine lxx is equal to 0. This implies that, what are the solution to this? Tell me your answer. If I ask you sine x is equal to 0, how would you solve for x? What is the solution of x? Well, x is going to be equal to n pi, right? So the solution is basically what you have inside is just going to be equal to, so lx times x is equal to n pi in order to satisfy what we have here, where we have nx, where nx is equal to 1, 2, 3, blah, 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 blah. So we have this, and then if we just isolate our, if we just isolate, wait, I think I'm plugging the wrong thing here. Okay, because I had kx here, so I should have kx here, but somehow I think I was thinking too much that I forgot to copy, and I was copying the wrong thing. So kx, so this implies kx is equal to, yeah, let's just rewrite this. This implies kx times lx yeah, because we plugged in our lx here, right? When we have lx here, we should have replaced our x with lx. So let's replace it and fix it. So we have kx times lx inside, not lx times x. So kx times is equal to nx pi, where nx is equal to 1, 2, 3. Again, I apologize for what I did here, because you might have seen the videos on my main page that I have problems syncing and writing at the same time, and often that when I write I cannot sync, when I sync I cannot write, or I write the wrong thing, and that just happened right there. But let's not talk too much about that. So if we just isolate our kx, so kx is just going to be nx pi over lx, where nx is equal to 1, 2, 3, blah, blah, blah. let's move this here a little bit so we can write for ky too. So ky follow the same logic. So ny pi ly, where ny is equal to 1, 2, 3. Kz is equal to nz pi lz, where nz is equal to 1, 2, 3, blah, blah, blah. So we have obtained this expression for kx, ky, and kz. So what are we going to do next? Well, next, if we recall, if we go back for our energy, at one point we did for this, right? We look at this term. So let's copy it and paste it here. You can realize what we can do here. We can simply plug in our find kx into here, find ky into here, find kz into here. So this is going to give us E is equal to h squared over 2m and x pi over lx. And then remember, this is all squared, so don't forget about that part. Almost forgot. And y pi ly squared plus and z pi lz squared. And if you take the pi out, right, what you get individually for this is n squared x pi squared over lx squared. So we can take all the pi out of the equation, so we just get the formula h squared pi squared 2m times nx squared lx squared plus n squared y ly squared plus nz squared over lz squared. So this is what we have for the energy, where nx and y and z are positive integers. Is what we have here. So now we have to do the normalization part. So for our wave function, let's write this again. So psi xy, z is equal to xx, y, zz. We've written this multiple times. So we already found the solution to it. Right, for xx, it's just going to be ax, kx, x. So for xx, it's going to be ax sine kxx. But our kx here is going to get replaced by this nx pi over lx. So nx pi times x over lx. And our yy follow the same logic. Sine ny pi y ly. Our z is going to be a z sine nz pi times z over lz is what we have here. I think this is right. And what we're going to do here is that we have to look at our normalization condition. Remember, for any wave function, we normalize it, right? For example, for 1D wave function, this will just yield 1. But we have to do this for this equation here, which is a combination of all of these. So how do we do that? First, we're gonna have 3 integrals, each correspond to x, y, z. So the total probability of finding the particle inside the box must be 1. So our normalization is going to look like integration from 0 to lx, 0 to ly, 0 to lz, psi and x and y and z, x, y, z squared. Don't forget the square. Dx, dy, dz for our 3 different variables equal to 1. And this inside is going to be ax, ay, az. If we take the constant now, sine nx pi x lx, sine ny pi y ly, sine z pi z lz. And if we just call this constant ax, ay, az 3c, then what we really get out here is going to be so if we've called this c and we plug this into this, what we get out of this whole thing is integration from 0 to lx, 0 to ly, 0 to lz. Since we have the square root, so c squared sine square nx pi x lx, sine square ny pi y ly, sine square nz pi z lz. So this is what we have here. Oh, I forgot the dx, dy, dz is equal to 1. So this is what we have here. And we're going to have to solve it. So now the part is separating the integral. So we have to match our dx to our, and match our dy to y, match our dz to z. I've done this in my previous video when I did the exchange force. We did the same thing, right? So first we know, well, c squared is going to be a constant, so we can take it out of the entire equation. We have written so much already. If you guys are still following, congrats. You have made it much further than a lot of people. A lot of people would have gave up midway, but so let's just keep on going. We'll finish soon. So we take c squared out. So we have 0 to lx. So the first part will be sine x, sine square, nx pi x over lx dx, and the second part will be in terms of y. So integration from 0 to ly, sine square ny pi y ly dy, 0 to lz, sine square and z pi z lz dz is equal to 1, this whole thing. And if we just look at this, just take a look at this function. So 0 to lx, sine square nx pi x lx dx. So if you have known that the integral of sine kx over a full period is a well-known function, so that's 0 to L, from integration from 0 to L, sine square m pi x L dx is equal to L over 2. So this is a well-known full period function from math. So what does this result tell us? Well, this result tells us that our L is going to equal to Lx in this case, and our result of this integration is just going to be Lx over 2, right? Because L over 2 and then L is Lx. So the result for the first integral is going to be Lx over 2. Second integral is going to be Ly over 2. Third integral, Lz over 2. All follow the same logic. So what are we left with? Well, we're left with c squared, right? Still here, times our times are 1, 2, and 3. So times our Lx over 2 times Lx over 2. Ly over 2 times Lz over 2 is equal to 1. Don't forget that the 1 at the end. Further simplify this, c squared is equal to Lx Ly Lz 2 times 2 times 2, so 2 to the power of 3 is 8. It's equal to 1. And our c squared is equal to 8 over Lx Ly Lz, right? So therefore our c is just going to be the square root of a over Lx Ly Lz. So finally, we have to obtain the solution after all of this long hour of work. So psi nx ny and z is equal to xyz. XYZ, I forgot. This is the variable, now it's equal to xyz. So the final expression is we have normalization constant at front, so 8 over lx y lz times sine nx pi x over lx sine ny pi y over ly, and finally sine nz pi z over lz. So this is finally what we're gonna have, and you can see if you check the textbook that it matches exactly with what the textbook have, right? And you can really just see how much step the textbook had skipped just for this normalization wave function, because it sort of assumed that the student already has a fluent idea of differential equation. All of this math foundation is really solid, but even for better foundation students, they still need to sit down and think about this and grind this out themselves. But if you follow my tutorial, I don't think I skip any steps, and I sort of just reached this end. And there's also the allowed energy formula, which I think I already written like 3 pages ago. So I think the allowed energy I written was here, right? This is the allowed energy, and it matches what the textbook gives too. Yeah, and k here is the magnitude of our wave vector. Just some addition. So k is equal to kx, ky, and kz. And that is gonna be our this video. That's gonna be the end of our this video, because in my next video I'm gonna continue the calculation and go all the way through and then end up with the final formula. But that is for the next video to discuss. And if you have learned anything, please like and comment down any questions you have, and I'll see you in the next video.